In this, we are going to review the Laplace transform technique using the definition. So let's look at the definition first. So if we have a function which is a piecewise continuous function, so we need to make sure that it's piecewise continuous just to make sure that we can integrate. And also we assume that it's of exponential order. So why we need the exponential order? So we again make sure that it's exponential order just to make sure that the function grows slower than the exponential function. So we have exponential function here. So we're going to make sure that ft grows slow compared to that because you can evaluate the function in infinity. So we'll make sure that this integral exists. So for that we assume those two conditions. And also we assume that s is positive because you can see that there's a e to the minus st term. So if s is negative, this is going to grow indefinitely, the exponential. So we're going to make sure s is positive because of the negative sign. Okay, so this is the definition of the Laplace transform. So it is from 0 to infinity, e to the minus st, ft dt. So you can multiply by e to the minus st and integrate. So, and then how to integrate? So normally, if you get a problem like that, we use integration by parts. So integration by parts would be the major technique for Laplace transforms. So in short, we say IBP. And also, sometimes like we are not going to do it the long way, and we sometimes use the shortcut. So a shortcut, what we normally call the DI method. So if you are not familiar with those two and you need more practice, and you can find link in the description so that you can practice those techniques first, and then you can use them in the Laplace transform technique. Okay, so let's look at the first problem. So we have the Laplace transform of 4. So directly we can use the definition here. So the definition is 0 to infinity. So we have e to the minus st times 4 dt just by the definition. And then what we can do is, you can see 4 is a constant, so you can pull it out of the integral. So we have 0 to infinity negative st dt. And then what we can do, we can use here, like when you integrate with respect to t, s act like a constant. So that means we can use this formula. So we know the formula, which is e to the kx dx equal 1 over k. So k is a constant, e to the kx plus c. So that's the formula. That's the like formula to learn in Calc 1. So we know same formula, but here the variable is t. So with that, so we can use that formula. So that means we can write this one as 4 times, you can see negative s is a constant, so it is s, you can write the negative sign up there, and then e to the minus st, and you evaluate at infinity and 0. So let's look at the behavior of the exponential function, and you know that, and we assume that s is positive. So assume s is positive, and you know the graph of the exponential function, which start with 1 and then decay. So that's the graph of the e to the minus st for positive s, and you can see it's gonna go to 0 at infinity. So because of that, what happened? If you evaluate the two functions, the function at those two endpoints, you can write this one as negative 4 over s, and then you can see if we at infinity this goes to 0, the function goes to 0. This part goes to 0 at infinity because of this graph, so it is 0. And then when you plug in 0, and then we know that e to the 0 is 1. So because of that, you get negative 1. And then if you multiply through, so you can see that you get 4 over s as the answer. So that is the Laplace transform of 4. And then under the condition s positive. So we assume that s is positive. Okay, so let's look at the next one. So as a second example, we're going to look at ft equal e to the negative 2t. So again, so it's a Laplace transform of ft. It's e to the negative 2t. By the definition, it is 0 to infinity, e to the negative st, and then e to the negative 2t and dt. So what we do in this case, actually we can combine these two into one. So that's the trick here. So we write this one as 0 to infinity e to the, you pull the negative sign out, and if you do that, you can write this one as s plus 2 t dt. Now, as in the previous example, we can use the same formula here because s2 is a constant, so it is e to the kx formula dx. So so it is e to the, so 1 over k e to the kx plus c. So that's the formula we're going to use with the t variable. So that means this is going to be as before, negative sign we write in front, so it is 1 over s plus 2, and then e to the negative s plus 2 times t, again evaluated at 0 and infinity 0. And then again, so what happened here, so you see you have s plus 2 terms, you want to make sure that that is positive. So that means we can assume in this case, so we can assume s is greater than negative 2. Why we do that? Then you can see s plus 2 is greater than 0. So that's the assumption. So under that assumption, and you can see e to the negative s plus 2 t actually goes to 0 as t goes to infinity. So we need that, and then again the graph is, so it's just like that when t goes to infinity. So that's the graph of e to the minus s plus 2t. Okay, so because of that, now we can evaluate as before. So it is negative 1 over s plus 2, and then at infinity it is going to be 0, and if you plug in 0 it is 1 because e to the 0 is 1. And then when you multiply through, so you're going to get 1 over s plus 2 as the answer under the assumption that s is greater than negative 2. So that's the solution for this one. So let's look at another one which is very similar to this. Suppose we have if t equal e to the 2 plus 3t. So with the Laplace transform of e to the 2 plus 3t, so which is by the definition 0 to infinity e to the minus st e to the 2 plus 3t dt. So in this case we can do a little bit of algebra. So you can see e squared is a constant, so you can pull it out of the integral, so that you can write this one as e squared, and then 0 to infinity e, as before we're going to pull the negative sign out and then write this one as s. Because of the plus 3, since you pull a negative sign out, you can write this one as a negative 3. So this is what happened. So you get two negative signs, and then dt. And then after that you can see this problem is very similar. So we can assume that this is positive, so that means under assumption is x is greater than 3. So under that assumption we can do a similar evaluation here. So that means it's going to be negative 1 over, so you can see actually we still have the e squared, so we can write that. So this e squared, and then times, so you can see s minus 3, negative sign we write up above, and then e minus s minus 3 t, and evaluate at infinity and 0. So we use the same argument here. So it is you can say negative e squared s minus 3, and then if you, when you evaluate what happened at infinity, under the assumption s is greater than 3, you can see this goes to negative infinity, so the whole term goes to 0. And when you put 0, this exponential term goes to 1. So that's what you get, and then when you multiply through, you can see that you get e squared over s minus 3 as the answer under the assumption that s is greater than 3. So that's the solution for that. So let's look at the next one. So let's look at a special one. How about so let's see the next one. How about if t equal e to the t squared. So one thing you notice that e to the t squared grow much faster compared to the e to the t function. So e to the first order. So you can see that this is not of exponential order. Not of exponential order. So that means there should be a problem here. So when you try to integrate, so it's not exponential order. So let's try to see what exactly happened. So and then because what is not exponential order means, if you look at e to the t squared, you cannot bound this function by an exponential function. So you cannot find k and c such that e to the t squared is slower. So the reason is, if you look at the graph of these two, e to the t squared grow like this, and then k e to the ct. So k is like just a constant, so it can be anywhere. I mean, if you look at that one, so it can grow a little slower than that, so it's still exponential. It can be like this. So you can see after some time, the e t squared grow much faster compared to k e c t. So that's the problem. It's going to grow much faster. That means the integral does not converge in this case. So let's look at the integral and see where you get the problem. So let's start with the definition, which is e to the t squared. By the definition again, it is 0 to infinity e to the minus st and then e t squared dt. So we combine them as before, so it is 0 to infinity e, so you can write this one as t squared minus st dt. Now what we can do, we can use the completing square technique. So we can write this one as 0 to infinity e. So you can write this one as t minus half of the coefficient squared. So when you do that, you can see you get t squared and minus st, but you also get s squared over 4 term. That means you have to subtract that term to match them. You can see they match, and dt. But you can see e to the negative s squared of 4 is a constant, so you can pull it out of the integral. So you can write this one as e to the negative s squared over 4. And if you write the rest, 0 to infinity e t minus s over 2 square dt. Now the problem is, you can see this integral does not converge. This one does not converge. Does not converge. The reason, it is like e to the t squared, with just like a shifting, just a shift, so it doesn't change much. So that means this integral does not converge. So that means this one does not exist. So this integral does not exist. So that is the reason why this integral cannot exist. So that means the Laplace transform of e to the t squared does not exist. So the Laplace transform of e to the t squared does not exist. So the reason is this exponential function grow too fast. This one grow too fast. So yeah, so this function grow fast. So that's the reason why it can converge. Okay, so that's the situation where you cannot actually find the Laplace transform. It's a good to know, like remember like at least one example like that. Sometimes it's important to know like when you can do and when you cannot do. Okay, so let's look at the next example. So let's look at this one. So Laplace transform of 2t minus 3. So again, if you write the definition, so you can see that this is 0 to infinity e to the minus st. So you get 2t minus 3 dt. Now when you look at this problem, and you can see this is a familiar problem from Calc 1. So what we do is use the integration by parts. So use the integration by parts or the shortcut. So normally like shortcut comes really handy in a situation like this. So it's a shortcut. So let's see how to use a shortcut. What we normally call the DI method. So what we do, we're gonna figure out which one we're gonna pick as the derivative part. Which one we're gonna go for the integral part. Normally we pick the derivative one is the one that easy to take the derivative, and the other one is the integral one. So we can write this one as di. So it's a d, the derivative one, and the integral one. So the derivative one, we normally, in a polynomial, we normally pick the polynomial part as the derivative, because once you take the derivative, it can disappear. That's the whole point. And this is e to the minus st. So we take the derivative, this is going to be 2. If you take the integral, we did this before, so that means this is going to be a constant, act like a constant, so it is negative 1 over s e to the negative st. And if you take the derivative again, this is going to be 0, so that means the integral will stop there. And then this one going to be 1 over s squared, because you multiply by another, you can divide by another negative s, so you get this. And then what we do after that, the first one is a plus sign, and then you switch the sign, so next one is a negative sign, and the integral can stop there because of the 0. Okay, so that means you can write the integral now like this. So it is going to be negative, so you can multiply. So we write this one as negative. So if you multiply the first one, so you get negative 1 over s, and then we have 2t minus 3 e to the minus st. That is the first product. The second product is still negative, so it is going to be negative 2 over squared e to the negative st. And again we can evaluate this as infinity and 0. So then how to integrate this one, and how to evaluate this one? And you can see we have this exponential function in both with the negative sign, and we can assume that st is positive. We can assume it's positive. So if st is positive, so we have this e to the negative exponential function. That means that's going to dominate this whole product. So that means this is a polynomial. So when you have polynomial, always the exponential function going to win with the polynomial. So that means because of that, at infinity, this is going to give you a 0. So it is a 0 at infinity. And then when you plug in the 0, you know that e to the negative st going to give you 1. So because of 1, you only get the other terms. That means from the first one, because see, you can see that there are negative sign. So because of negative sign, the second term going to be positive. It's going to be plus. And when you plug in 0, it is 0 minus 3 over s from the first term. From the second term, you get 2 over s squared. That's the second term. So if you simplify, you're going to get 2 over s squared minus 3 over s as expected. So from the tables, and you can see that that's exactly what you're going to get. And then from a direct integration, and you can see you get the answer like that. Okay, so let's look at the next one. So we have, we're going to find the Laplace transform of 4t cubed minus 2t squared plus 5 using the definition. So again, we write the definition here as a 0 to infinity, e to the minus st, and the expression. So it is 4t cubed minus 2t squared plus 5 dt. And then again, for this one, we're going to use the shortcut. So we're going to pick this one as the d part and the rest as the I part. So let's write the table. So it is d and I. So we have 4t cubed minus 2t squared plus 5. That's the first term. And the other term is e to the negative st. So take the derivative of the first one, which is 12 t squared minus 4t, and if you integrate, you're going to get negative 1 over s e to the minus st, and again take the derivative, so you're going to get 24t minus 4, and if you integrate, you get 1 over s squared e to the minus st, because you're dividing by another negative s, so sign a switch. And if you take the derivative, you're going to get 24 here, so you're going to be negative 1 over s to the cube e to the negative st, and you take one more to get a 0, so you get 1 over s to the 4 e to the negative st. Okay, it's complicated, but that's what you get. So again, so we're going to go with the sign, so it's a plus sign, and then we have a minus sign, and then we have a plus sign, and then we have a minus sign. So those are the terms we get. So that means we can write the transform now. So you can see it is negative. Start with the first one. So you're going to get this. You write the product with the sign. So you get all these product, and then you can evaluate at infinity and 0. And again, you can see that when you put infinity, because of these polynomial terms, they all go to, the whole product goes to 0 at infinity. And then at 0, when you plug in 0, all the t terms disappear, and then e to the st become 1, so you get this as the answer. So that means your final answer should be, from the first term, you get 5 over s, that's from the first term, and the second term you're going to get 4 over actually second term disappear because all these have a t, so complete disappear. The third term going to give you 4 over s cube, and the last term going to give you 24 over s to the fourth, and you can see this match with the answer if you get from a table. So that's the final answer you get for this one. Okay, so let's look at the next one. So as the next one, we can look at a piecewise function. So it's a slightly different example. So we know that the piecewise function defined as t minus 2. So you can see if t is smaller than 2, it's going to be the negative of that. So that means it's going to be 2 minus t if t is less than 2, and then it is t minus 2 if t is greater than or equal to 2. So that means it's going to switch. So that means also if you look at the graph, and this is what you get, so you're going to go like that and like this, and at 2 it's going to switch the direction, so it is t minus 2. So that's the graph. That means at 2 is going to change. So because of that, what we can do, we're going to split this integral into two parts. So first we can write this one as, by the definition, it is 0 to infinity e to the minus st. So it is t minus 2 dt. So that's the definition. Now what we can do, we can split them into two. So we can write this one as 0 to 2 e to the minus st t minus 2 dt plus 2 to infinity e to the minus st t minus 2 dt. So you write it like that. And then you can see on the first part from 0 to 2, this one is negative t minus 2 because you want to make sure that you get a positive term. And the second part, this one is equal to t minus 2. So though, that means from 0 to 2 is going to be e to the negative st 2 minus t dt. And in the second one, from 2 to infinity, it is e to the minus st. It is going to be t minus 2 dt. So that's what happened. So I'm going to switch the terms. Now what we do, we integrate term by term. So this is very similar to the example number 5 that we did. So we can use the integration by parts, the shortcut method for this one. So let's look at how one of them going to work. So what I'm going to do, I'm going to do this one first, because you can see the other one is just switch the sign. So let's draw the table. So we have d and I. So what you get is t minus 2 for the first one and e to the minus st for the second one. So if you integrate, you take the derivative, you get 1. So this is going to be negative 1 over s e to the negative st, and the second one, next line is 0. So it's 1 over s squared e to the negative st. So we know that this we did multiple times. So that means if you look at the integral, so you can see it is going to be it. So we don't put any values here. We just write the integral. So it is the minus st t minus 2. So the other one is just a negative. Dt is, so you can see this is a plus 1, this is a minus 1. So because of that, so you can see you're going to get negative t minus 2 over s e to the minus st. That's the first term. Second term is also negative, so it's a 1 over s squared e to the negative st. So that is what you get as the integral for this one. Now what we can do, actually we can also simplify this a little bit. So you can write this one as equal to, if you simplify this, you can pull the e to the negative sign out with the negative sign. So it's negative e to the negative st you can pull out. So if you do that, you're going to get t minus 2 over s plus 1 over s squared. So that's what you get as the integral. So now what we can do, we can go back to the integral and substitute for those two. So let's try the answer now. So it is going to be, so we have the two integrals. You can see first one going from 0 to 2. The second one going from 2 to infinity. But and then this one is the integral that we evaluate. But the next one is just the negative of the value expression, because you can see this term switch the sign. So that means you can write this one as, so the first one you can write as, remember we had a negative sign, so it becomes positive now. So it's e to the, so we have e to the minus st, and then we're going to get t minus 2 over s plus 1 over s squared. But you can evaluate this one as 2 and 0, the first one. And the second one, now we have a negative sign here, e to the minus st, but that's what you get. And then here we have again t minus 2 over s plus 1 over s squared. This one we can evaluate at infinity and 0, infinity and 2. Infinity and 2. So let's evaluate them. So the first one, you can see when you plug in 2, the t minus 2 term goes to 0. So that term disappear. And then you're going to get e to the negative st. So you get e to the negative 2s. So you get 0 from the first term, 1 over s squared from the second term, minus, when you plug in 0, you can see that you're going to get negative 2 over s from the first term, and then 1 over s squared from the second term. So that's what happened for the first integral. From the second integral, and you can see when t goes to infinity, you get a 0 for the whole expression, and when, from the second one, and then you can see minus. When you plug in 2, the t minus 2 goes to 0 as before, so you don't get anything from that. But from the second term, you're going to get e to the minus 2s and then divided by s squared. So times 1 over s squared. So that's what you get from the second term. Now what we can do, we can simplify all of them and we can combine them. So when you combine, you finally get 2e minus 2s over s squared, and then you're going to get plus 2 over s term here, and you also get a minus 1 over s squared term. So that's the other term, this one. Okay, so that's the final answer you get for this one. So you can do something like, so what we did was we split the integral into two parts. Okay, let's look at the next example. So as the next one, let's do this classical problem. So what is the Laplace transform of sine 3t? So like some constants. It can be any constant here. So let's see what's going to happen by the definition. So we can use the definition again. So it's the Laplace transform of sine 3t, which is equal to, by the definition, 0 to infinity e to the negative st sine 3t dt. So what we can do, we can use shortcut for this one. So let's use a shortcut. So use the integration by parts or the shortcut. Shortcut gonna be very easy for these kind of problems. So we're gonna do that. So we can write the d and I. So we have d and I. So for these kind of problems, it doesn't really matter which one you're gonna pick as a d and I. So we're gonna go with the exponential part here, st, and then sine you're gonna write here. Even if you switch, you still get the same answer. So now we take the derivative of the first one, so which is negative s, because like a constant, so you can write it like that. So negative st. When we take the integral, so it is negative 1/3 cosine 3t. That's the integral of that. Sine means negative cosine, and then 3 you divide by that. Okay, and then we take one more derivative. So it's going to be s squared e to the negative st. This one going to be 19 sine 3t, and we're going to stop here. The reason is, you can see this is plus and this is minus, and then you can see you get the same integral again. So when you see a cycle like that, you can stop there. So now how to write the answer? This is how we write the answer for this kind of one. So we can write this one like this. So we're going to say e to the minus st sine 3t dt equal. So if you look at the first product, that's going to give you negative 1/3 e to the negative st cosine 3t. That's the first line. Second line going to give you negative s over 9 e to the negative st sine 3t, and the last one is the integral, because the last one is going to be the integral, so which is s squared over 9, the integral. We don't put values here, so e to the negative st sine 3t dt. So that's what you get from the last line. Now what we're gonna do, you can see this the first and this one is the same, so we're gonna move that to the other side. So when you move that to the other side, you can write this one as taking the common denominator, you can write this one as 9 plus s squared over 9 the integral, so which is e to the negative st sine 3t dt. On the other side, you can see you can pull the negative sign out, and you can also pull e to the negative st out. Common denominator is 9, so you can write this one as, if you combine them, you can write this one as 3 cosine 3t plus s sine 3t. So you can write it like that. We are not going to add the plus c here because these are definite integrals. Okay, so that's what you get. So that means we can plug that back into the expression, and also you can see that if you solve for this integral, so the 9 get cancelled out, and then you're going to divide both sides by this expression, s squared plus 9. So because of that, your integral going to be now original integral, which is negative e to the negative st, and in the denominator you're going to see that s squared plus 9 term because you divide both sides. And then we have here 3 cosine 3t plus s sine 3t. You can evaluate at infinity and 0. Now when you evaluate, see what happened. So you can see it's a negative. When you put infinity, the whole expression is gone because of the exponential order, because this is gonna dominate and this grows slow. So that means gonna at infinity it is 0. So that means so you're gonna get negative. So at infinity is 0. So it's gonna be negative. I'm gonna pull the s squared plus 9 out. So at infinity, it's going to be 0, so that term is gone. And then at 0, so it's 0 at infinity minus, and at 0, what will happen is you can see the cosine going to give you 1. Cosine going to give you 1 at 0, and then sine going to give you 0, so that term disappear. So that means you're going to simply get negative 3 from the first term. So if you simplify this, and then you can see that what you get is 3 over s squared plus 9 as expected. So that's expected result. 3 over s squared plus 9, and that's what you get. So this is how you kind of do a problem like that when you have sine or cosine. So we do the same thing like this. Okay, so so just practice this one and see, like, you know, how all those steps like nicely turn out to get the final answer. So let's look at the next one. So let's look at this piecewise function. So what it says that, so it is from until 2 it is 0. So until 2 it is 0, and after 2, so what will happen is it's going to jump. So it's going to be the function t. So how you draw it? So you can see it is t. So so it's going to grow like this. So it's going to go until so it's a line. So it's a line until 4. So it's going to pass through 1. It's going to go like that, and that's until 4. So at 4, so it's going to be 0. After that is 0. So that's the shape of the function. So the question is and pass through 0. So the question is how to find the Laplace transform of this one if you have something like that. So we again use the definition and see how we can get the answer for this one. So so the Laplace transform of ft by the definition, so it is 0 to infinity e to the minus st ft. And then what we do, we can split the integral into 3 parts right now, because there are 3 different regions here: 0 to 2, and then 2 to 4, and then 2 to infinity. So 0 to 2, 2 to 4, and 2 to 4 to infinity. So let's split them. So we have 0 to 2. You can see from 0 to 2 its function is 0, so you don't get anything from that. For the second one, you can see 2 to 4. So we have e to the negative st. The function is t in the region. And then, so just use the definition. And the next one, go from 4 to infinity, you can see function is 0 again. So, so that means you only get one integral here. So just get one integral, and so you're going to evaluate that. So for this one, just to know, so we can use the other technique. So we can use a long technique for this one. We're going to pick t as u and the other part as dv. So if you do that, you can write this one as u equal t and the dv equal e to the negative st dt. So it's du equal dt, and then v equal negative 1 over s e to the negative st. We're gonna not add the c, and then again you can still use a shortcut, but I'm just gonna do it just to learn, you know, the technique. So and then what you get is a negative. So we write the uv product, so that means it's going to be negative t over s e to the negative st, evaluate at infinity and 0. Actually not infinity and 0, those values are 4 and 2, 4 and 2, and plus VDU. So when you do the VDU, you get 1 over s. It can be plus because of the negative sign. You also see that there's a negative sign, so because of that, it's going to be plus. So 1 over s, and then go 2 to 4 e to the negative st dt, and then you can see this integral is again you can do because negative is act like a constant. So because of that, so you can see actually in the first integral you can actually plug in the values. So if you plug in the values, you can see negative s is common, so you can pull it out. So you're going to get 4 e to the negative 4s when you plug in 4. Then minus when you plug in 2, you get 2e negative 2s. So that's what you get from the first integral. Second integral, actually you can integrate again, so you get 1 over s squared. You get e to the negative st, evaluate at 4 and 2. So actually now you can complete the integral, and if you evaluate the integral and plug in the values and simplify, see whether you get this one. So this is what you should get as a final answer after you simplify, and you can see that there are negative e to the negative 4s terms here, and there are e to the negative 2s terms there. Okay, so this is the final answer. And later we can discuss a different technique if you get something like that. When you have piecewise function, we use an argument called switches. So you can use switches to get the answer. That's like a different technique. And yeah, so we can do the same problem using that technique, and you can match the answer, and you should get the same answer for that. Okay, so let's look at the next one. Actually, I'm going to give you another problem for you to try. So see whether so this one has like 3 pieces. So we have 3 pieces, and see whether you can get this given answer after you do a similar argument like this. So let's try this problem. So try to do this piecewise function as an exercise, and this is very similar to the previous problem, but we have 3 pieces now. So you can see until 2 it is 4, it's a flat. So if you look at the graph, this is what you get. And then after between 2 and 4, and you can see the graph is a line and that pass through 0, so you get this one. So you get the line between 2 and 4, and then the final part after 4 you get the exponential part. So what you do in this case, as before, you can split the integral into 3 parts. So you can write it like this. So it's Laplace transform of ft. So you can write this one as 3 integrals. So we have a first integral going from 0 to 2. So we have e to the negative st 4 dt. That's the first part. And the second one going from 2 to 4, you get e to the minus st t dt. And then finally you're going to go from 0 to infinity, which is e to the minus st e to the 4t, e to the t dt. So what we do, we can integrate all those 3 separately and see whether you get this as the answer. So this is the answer you're going to get. So see whether you can do those 3 integrals and get this answer. And also you can do this using the switches, and we do that problem in a different video using the switches, and you can get this answer much quickly. So yeah, so we're gonna do that in a different one. Okay, so good. So let's look at the last problem. How about we have a product? What do you do with the product? So let's try to do this one. So Laplace transform of 2 minus 3t e to the negative 4t. So again we use the definition. So it is 0 to infinity 2 minus 3t e to the minus 4t e to the minus st dt. So what we normally do, we can combine them into 1. So it is 0 to infinity 2 minus 3t e to the negative, so you can write this one as s plus 4 t dt, and then we can use a shortcut for this one, so we use the di. So if you do that, so you can see it is 2 minus 3t, and then e to the minus s plus 4t, take the derivative, so you're going to get negative 3 here, and this one going to be negative 1 over s plus 4 e to the negative s plus 4t, and then take the derivative again, so you're going to be 0, and if you take the integral again here, so you're going to be actually plus now, so 1 over s plus 4 to the squared e to the negative s plus 4t, and then we can use a sign, so it's a plus and a minus. So because of that, now you can write the integral, so that means your integral going to be like this. So these are two products you get, and you can evaluate at infinity and 0. And if you plug in the values and use in the exponential order, you can see at infinity they both become 0, and at 0 you should get 2 over s plus 4 minus 3 over s plus 4 squared. So under the assumption that s is greater than negative 4. Okay, so that's what you should get for this one. And then see whether you can do this as an exercise, and you will see that it's actually quite long, even though it looks simple. So t sine t. So try to see whether you can do this one. And you will say it can take a lot of stuffs because of the sine term here. So see whether you can do that, and there'll be another video that I'm going to discuss how to do this one. Okay, so thank you so much for watching.